right? Some of it is technology has changed, and I'm kind of keeping the class up to date with technology. And other times it's just there's a better way presented or stressing different things. Let me get this started. Yeah, I sometimes get notifications if someone leaves a comment, but you know, most of the ones I've seen are not that substantive. So I've mostly, I mean, there might be some I'm not seeing, but yeah, if there's stuff on there, the class message board and stuff is great for asking questions for me. Great. So let's get started. So everyone, so today we're going to be talking about Jaccard similarity, kind of like the notion of similarity in general, as opposed to a distance. Talk about some modeling of text with k-grams, and we'll get into minHashing. So this lecture is going to try and encompass what used to be kind of most of the opening 3 lectures of the course. This was a very influential approach that's kind of gone out of style in a lot of the areas I had used to try and motivate what was going on. So it's still used in plenty of other places, but I've kind of moved it back a little bit. So into the semester, and we're not going to go in as far in depth as we used to go when I taught this course. So before we get started, I wanted to kind of review just the schedule. Your proposal is going to be due on Wednesday. There's a Google Doc where you can fill stuff out. We've been filling out the group teams in there. I think we'll probably close that in probably today or tomorrow to try and kind of encode the groups into Canvas. So each group only needs to submit one document. So you can still form groups if you don't make it where we encode it into Canvas by the time you submit, then everyone in the group should submit the same thing and we'll know to group you together. People still haven't found groups. Is anyone still looking for a group? Okay, great sign. But if there are people online who are still looking for groups, haven't found them, we will try and pair you up afterwards, and you will lose some points on the first part of the project assignment. Okay. Okay, so that's coming up. The other thing is the second homework. I just want to circle back to this and kind of, again, it's exploring these high-dimensional word embeddings and the different distances between them, and trying to get you some experience in using some of this nearest neighbor search. And I want to, again, tell you that for some of you, this first 2A will probably be the most time-consuming part. If you have everything properly installed, it should be pretty easily, but if you don't, may take some while to get stuff installed. I encourage you to go to the TA's office hours, which are today after class. If you have questions with this or post questions on Canvas, if you have questions about it, it can be, installation sometimes can be a bit tricky. Once you get it running, it should be pretty easy to use. This is, this has recently become much more mature technology. It's become central to a lot of things. So I think it's really get used to using this sort of thing. It's very useful in lots of applications for speeding up kind of this nearest neighbor search, which is kind of a very fundamental operation. In that context, kind of the lecture on Wednesday last week, the only lecture last week, was on kind of this approximate nearest neighbor search. using the hierarchical navigable small world stuff. We eventually got to this. I got some feedback after the lecture. Some people were kind of intimidated by the amount of data structures in there. If you hadn't had a serious data structure course or hadn't had one very, very recently, it's probably the most data structure intensive lecture we'll have during the semester. We'll mention data structure and scalability issues through a lot of other kind of lectures, but this was mostly on how do I, pre-process data so I can do these operations quickly. So very much some kind of key technology to understand roughly how it works, and hopefully a little bit historical context of where we got to and maybe why that was kind of was surprising. You don't necessarily need to know all the details of the data structures trials, trying to give some context for these things. You'll need to know what the capabilities are, and through the homework, get familiar with using those sort of capabilities. That's the main takeaway, that this is a problem that used to be thought was intractable and is no longer intractable. And so it's kind of opened up a bunch of things. Okay, so we're going to be talking the next two lectures as kind of an alternative to this way of doing fast, scalable nearest neighbor search, through getting through a different way of modeling through locality-sensitive hashing. Locality-sensitive hashing used to be what we thought was the solution for this. It doesn't work as well as the graph search-based approaches in practice. It is more interesting from a modeling perspective in that there's more modeling that can go into it. You can apply it for more abstract sort of objects more directly. Whereas with the hierarchical navigable small world stuff, the HNSW, you basically need to convert things into high dimensional vectors and use either Euclidean or the cosine distance with them. If you want to use a different way of measuring distance, well, either you need to convert it into a representation where the one of those distances makes sense, or you could use locality-sensitive hashing in some cases. Okay, so it's a bit more general of a modeling tool. It is more randomized and it has overhead because of that. And so we'll kind of get to try and understand that, and I'll mix it in with some other kind of modeling topics as well. Okay, so hopefully, any other questions on the lecture from last Wednesday? I felt there was a couple people came up to me afterwards. All right, if there are, feel free to kind of reach out to me and find a time to kind of ask questions after class or office hours. Okay. Let's see. Oh, I linked to this kind of this article. It's basically a blog post, or do people even know what a blog post is? It's a blog post by someone who's probably too senior to know how to actually have a blog. But this was by so Richard Sutton, who recently won the Turing Award for reinforcement learning, and he commented on this bitter lesson you learn in doing large scale, in doing data analysis, where people try to model things very carefully, but then there are certain things which kind of win out in the end through more scalability and compute power added. But there are only certain types of things that can scale this way with more data and more compute. One of them is kind of supervised machine learning, he mentions. The other one is doing search. Okay, doing search and nearest neighbor search for finding a nearest query, and most similar thing, and doing prediction based off of that, or doing data mine based off of that. That's also turned out to be very, very scalable with more data to draw richer conclusions. So that's why I thought I would link to this. This was showing up on sort of nerdy social media I pay attention to. So I thought it'd be fun to link to that. It's a fun article to read. It's not very long. All right, so let's get into this. So I've got some pre-processed examples at some places, so I have some prepared slide here, but mostly I'll be still writing on the the iPad as we go. Okay, so I wanted to start out the differences between a kind of, we've talked about a D, which was, well, let's say from a D, which was a distance between two objects. Okay, so this was a distance, and we're going to instead today talk about a similarity instead, which is also going to be a function that goes from two things in a space and is measuring it on the real values. It's going to be plus, so that means, I guess I use slightly different notation. I said the real values would be greater or equal than 0. That will almost always be true here as well. This would be a similarity instead of a distance. And I bring this up because some things, including what we'll talk about the next couple most of the next couple lectures, will be more natural to think of as a similarity instead of a distance. And so kind of just to kind of put a table to compare these, this quantity is small if the pair of objects A and B are close. But whereas the similarity, this is large if the pair A and B are close. And it's a different way of quantifying this, but it's kind of changed the order, right? It used to be if a distance is small, things are close. If things are very similar to each other, that means the similarity is large. So if they're close to each other, the similarity is large. So if it's large if the pair is close instead. So this is kind of an inverse of a distance in some way. And so again, and similarly, this is, and it's large if far, and this is small if far. Okay. So again, with the distance, it's usually 0 if A is equal to B, right? So this was, if it's a metric, it has to satisfy this. And so it's usually, for a similarity, we usually try and set it so that it is a value of 1 if A is equal to B. So we often scale the upper bound of the similarity. So if they're they're exactly similar to each other, similarity would be 1. Whereas the distance, if it's large, can go off to kind of infinite. Sometimes if things are very, so what this means is that the distance is usually in the range 0 to infinity, where the similarity is usually in the range of 0 to 1. Again, so this won't always be true with the similarity, but this will often be the case. And we can often convert between them. There are two ways to convert between them. DAB will be just 1 minus the similarity. Okay. So the distance between 2 points A and B is equal to 1 minus the similarity. The stuff we'll talk about most of in the next lecture, that will be true. But this will give you a distance between 0 and 1. Okay, so there's another way to convert between them, which is a bit more complicated to write down. Let me write it down and we can comment on it. This is, so the similarity between A and A plus the similarity between B and B minus 2 times the similarity between A and B, the square root of this. Okay, so this is the other way to convert between them. Okay, so this can potentially give you a distance between 0 and infinity. This allows for similar values to include some scale notion of the points. The common similarity where this would make sense is the Euclidean dot product. If I use the dot product as a similarity between two vectors, then I get back the Euclidean distance. This is exactly the Euclidean distance. If I normalize the vectors before I do this, then I'm measuring I think then I'm getting so then I'm just measuring something like the angle between them, the cosine similarity between them, and I get back Euclidean distance, but on things that have been normalized. So then the distance can only be between 0 and 1 again. So if I remove the scale quantity of the individual items, then I often get my similarity in this range. Okay, so there are different ways you can think about this trade-off, and depending on your definitions, you may want to use either one of these. There's a family of similarity measures where you can convert them this way, the first way, 1 minus s, and you can get a distance which is going to be a metric. That's going to include the Jaccard similarity, which will be most of the focus of today's lecture. Okay, the Jaccard will use the first kind of conversion, and you'll get a Jaccard distance by doing this conversion. Again, if you have a dot product similarity, then this gets you the Euclidean distance. And there are other things that can fit in this pattern. We won't talk about them all in the class, maybe some of them. Okay, so you've probably heard of the word similarity, kind of just the way people use it in the English language. But this is kind of mathematically what we mean. It's not quite as common as a distance in mathematics, but it's kind of a very similar notion. Yeah. Because yeah. So if you have a dot product of a vector which is a unit vector, right? Then the similarity in itself is always exactly 1. But if you have a vector which is not a unit vector, right, then the dot product with itself captures the squared norm of the vector. And so the squared norm of the vector A plus the squared norm of vector B minus 2 times the inner product and the square root, because these are all squared terms to get the units right. So yeah, if you'll plug stuff in here, and if you play with it a bit, it'll kind of make sense. We'll see if you have a kernel. You measure similarity with the kernel, like kernel methods in machine learning, like a Gaussian kernel. You'll use this one to compute a distance. And we'll talk about that maybe a little bit on Wednesday if we get to it. Where there's a family of things like Jaccard distance that work in this notion, that work with locality sensitive hashing. But yeah, it's about, I don't know, it's about half and half which one you want to use to create the distance. And so if you have kernels, for instance, and they're positive definite kernels, and you use this notion, then you get almost always get a metric back. So there's kind of a bunch of really nice mathematics around this. Okay. So what is the Jaccard distance or Jaccard similarity? Okay, and who's heard of Jaccard similarity before? Okay, this is something notion you've heard of? Okay, a few people. This is defined, instead of between vectors, is defined between sets, right? So you have two objects. I'll give some examples: 0, 1, 2, 5, 6. Okay, these are sets. And if you remember, when you write, if you've taken a discrete math course, when you have sets, you describe with these curly brackets, and as items separated by a comma, that means it's a set of these items. Okay. I've used just numbers here. These don't mean anything yet. In the next few slides, we'll put some more concrete meaning to them, but we'll just use numbers as placeholders here. And so I use this kind of annoying notation where I said the similarity between some script x cross some script x is a real value greater than 0. Well, this space of objects is defined for Jaccard distance is the space of sets. Okay, I haven't said what the universe, the space of sets is over, and in fact, I don't need to. Just something very convenient about the Jaccard distance. But it's the space of sets, okay? Or the Jaccard similarity, okay? And so now I can define the Jaccard similarity between A and B. Now this is defined using kind of some set notation. So I'm going to look at A intersection B. Okay, the cardinality of that, so the size of the intersection divided by A union B and the size of that. That's what the Jaccard similarity is. Okay, I can think about having two sets. This is, you make them a little bit closer. This is B, this is A, right? What is the intersection of the two sets? The intersection is this region up here. So that is the intersection of A and B. And then I'm going to divide this by the union of A and B. So let me draw them again in these Venn diagrams. And the intersection of them, or the union of them is going to be everything inside of A or B, right? Okay, so people have seen these Venn diagram notions before, intersection and union. This just gives a similarity between, I look at the size of the intersection divided by the size of the union, and this kind of tells me how similar are the sets A and B. Okay. Right, so, okay, let's just verify that this value is, the value must always be between 0 and 1. Right, so the Jaccard similarity must be between 0 and 1. Well, there's nothing negative about it, so it has to be positive because I'm just the ratio of two positive values. Okay, to be so it's got to be positive. That means greater or equal than 0. It could be 0 if the intersection is empty. If the two sets do not intersect, it could be empty. And it's less than 1. Less than 1 means the numerator is always smaller or equal to the denominator. Well, the intersection is always smaller than or equal to the union of two sets. Okay, so it's between 0 and 1. Okay, so this is kind of like we wanted here. And if I look at this example, let's look at the example where we actually look at the numbers here. Okay, this will be the intersection of the two sets is going to be the elements which are in both sets at 0, 2, and 5, right? So that's the intersection. We're going to look at the cardinality of it, and we're going to divide by the union of what's in the two sets, 0, 1, 1, 2, 3, 5, 6, 7, 9, and the cardinality of this, right? So the union included A had 0 and B had 0, but there's only a single 0 in the union, right? If something appears twice, when I combine them together, it only shows up once in the actual set. It's not a multi-set. It's a single thing here. And then so I'm going to count these values. The numerator, the size of the intersection is 3. The size of the denominator is 1, 2, 3, 4, 5, 6, 7, 8. Okay, size of the denominator is 8. And so this is the Jaccard similarity, 0.375. Okay, so these sets are kind of similar to each other. If they were much more similar, it'd be 1. If they were less similar, it would be much smaller number, right? Okay, so this somewhere in between. Okay, seems very reasonable to work with. Okay, sets. Why would I want to have a nice notion of similarity between sets? Seems like hopefully the last few lectures gave you some sense that vectors were actually very nice to work with. We can do a lot of nice things with them. The rationale for why we use Jaccard similarity was that we could model. Okay, there are two rationales, and we're going to go through both of them in this lecture. One is you can model text with them in a variety of ways. It shows up in looking at databases. You'll often have kind of categories of items, and you have things from different categories, and you want to say which categories are present. And it's hard. It's not necessarily the best way to measure this as a vector instead. So with in data management and in text, they're still used to model stuff. We'll cover the text way of doing it. The second way will be there was some efficiency in how we can process sets, which is, I'd say, is probably trickier than what we talked about with the high dimensional vectors even. It's a little bit, I think it's harder to wrap my head around how it can actually be efficient. We'll see this through minHashing. Okay, and minHashing will be the second thing we covered today. minHashing powered the first search engines. I'll do a lecture at the end of the semester on the history of search engines, which maybe is becoming outdated even. But like Alta Vista and Lycos, probably haven't heard of these things, but they were really cool pre-Google. And they were all powered by using Jaccard similarity, and minHashing to make this efficient. Okay, no one's heard of either of those search engines. Okay, man, life was difficult before Google. If you imagine what pretty soon, a few years, people say, what was life like before ChatGPT and stuff, right? It was fine, but maybe a few years and we'll look back and say it was kind of very different. It was very challenging. Okay, so let's talk about how to model text with Jaccard similarity. And so there is some of this is still used. Like I know if you've heard of retrieval augmented generation, which is where you often try and retrieve some documents to feed them to help provide answers for a query for like one of these chatbots. They'll often retrieve documents using something that models text, often with k-grams. At least a year ago, this was still the common practice. There's still some text retrieval methods that use some baselines that are very hard to beat for search engines, which use this kind of sort of modeling of text. Okay, so I've got some example text here with a lot of repetition in it. That's not too big to kind of give a sense of how this works. And so kind of the first baseline approach I want to describe is the bag of words model, okay, where instead of modeling text as a set, we kind of mentioned this before when we were talking about how we got to these like word embeddings, is that I would write down all the words I cared about. I had to write down all the words I cared about. In this case, they're only, I wrote down, I think this is 11 words. Okay, so this would be a vector in an 11 dimensional space. Is it 12? Okay, good. Okay, in a 12 dimensional space, I threw in the word zebra over here because zebra does not show up everywhere else. All the other words are showing up someplace. But in practice, maybe we have 100,000 words. I guess glove use like the glove I gave you had like 1.2 million kind of these of the subwords it looked at. Okay, but we're looking at 12 words here just to show you an example. And then what it did, it would take this as a document, not looking at individual words, but what's this whole document about? And said, how frequently did various words occur? So the word am shows up 3 times, right? So I'm going to write down a vector. Let me, this word am occurred 3 times here, am here, oh, am here. So this gives me the word 3. Okay, the word and occurred once. The word do occurred twice. The word eggs occurred once, and so forth. And then the word zebra occurred 0 times. Okay, so this would how you could represent this word as just a vector. That's called the bag of words representation. Okay, and so I'm just taking all the words and I throw them in a bag and I'm counting how many times each word appeared. And this was one way to represent the document. This did not work that well because it did not capture the context. In particular, if you have a word like not, which is saying so Sam did not like green eggs and ham, right? Did not like them. Well, that I don't know what the not is referring to. That's negating it. All I have, well, he likes something and it's about eggs and ham. So maybe he likes eggs and ham. I don't know what the not is referring to. Maybe it's, I am not Sam. I like green eggs and ham. I can't distinguish that text here. So there's no context between these words in this, the bag of words model. Yeah. I put all the words in the bag. I mean, I would, okay, so probably I would use like 100,000 words, but I'm not going to write those up in the slide. So I put zebra as a placeholder for the other 999,989 words that I did not put up here. Okay, so I would take a huge number of common words in the English language and you could build this way. Okay, so if you use a bag of words model or you use the models that these word vector embeddings are doing, you basically need to define which words you're going to be considering. With Jaccard distance, you don't need to do this. Okay. Okay, so I can also do this as I could think of having, I treat this as one big document, but now I can think of having 4 individual documents. And I can create the bag of words vector for each of the individual documents, right? So I am Sam, right? So I shows up here, here. It's showing up kind of twice in this last one, right? So am is showing up in these 3, and then Sam is also showing up in these 3. Okay, so now I can tell if I look at the two vectors v1 and v2 for documents d1 and d2, I say, oh, these are very, very similar to each other. In fact, I mean, I think they're the same. They contain exactly the same words. I am Sam. Sam, I am. They contain exactly the same words in them. They're indistinguishable in this bag of words model. Okay. Typically, you'd use this for longer documents like a web page or a news article. But in these very short document example, you can see it cannot distinguish between these two short documents. So the alternative to this is to measure this, the more complicated measure, using things called k-grams, and these are sometimes called called shingles. And so what we're going to do is we're going to model the document with these overlapping consecutive sets of words. So this would be one shingle, I am, and then the next shingle in this document is am Sam. So it's capturing, so I am. So now in the second document here, I have Sam I, and I also have I am. So it shares the I am, but the Sam I and the am Sam are different. Now I could recognize that if I look at these shingles, they're no longer the same. These documents are so no longer the same. These are k-grams of length 2. So it's 2 words in them. Okay. Let me see. I wrote, you can do all the k-grams of length 1, and this is all the individual words, treating this as a single document. And then if I do k-grams of length 2, I get all this set. I have I am Sam. If I treat it as a single document, I can wrap around the line. I can have Sam I. And I have am I. Why did this one not show up as a k-gram? Yeah, why did this not show up here? What? Because it's already in the set, because it's already here, right? So I'm going to model the k-grams. The standard way to do this, and it'll be because we're going to use Jaccard, is that I'm modeling it as a set of objects. I am already occurred here, so I don't need to put it in the set here again. Okay, so I'm treating this as one long document. Okay. Okay, so there were a bunch of modeling choices I put into here when I created these like the k-gram representation here. And I said, okay, this is the standard way to do it with Jaccard. What are the bunch of choices I made in how I did this? Yep. Yeah, so modeling choices. Okay, one is I wrap around lines and the sentences, right? I am Sam I am, I do not like I kind of blend the sentences together. I have am I. So if I have am I, usually I'm asking a question, am I hungry today? But I see that in the document because it's wrapping around the sentences. Maybe it's not good to span these across the boundaries of the sentences or the lines. This was a modeling choice. Okay. What other modeling choice do I have in here? Yep. So I've consecutive words. Sure, yeah. So I have Sam here, right? So I could say, well, if the word occurs twice, I don't want to write it down twice. Yeah, I think this could be a modeling choice to filter this out. That might be for other reasons, and I might want to filter it out if it's because I'm stuttering, then maybe I say a word twice. Well, maybe you filter that out of the of the context. All right, so yeah, that's another modeling choice. Yep. No punctuation, yeah. So no punctuation. Yeah, okay. See, I grew up with spell check, so I never learned how to spell. All of you are growing up with AI, so maybe you won't learn how to do something else. But all right, so no punctuation. So I did not capture the punctuation, which would have been nice. It would have marked the end of a sentence in here. It's hard to keep track. Do I combine it with part of a word? Do I treat a period as its own word? Right? These are questions I could ask, and this is a modeling choice. Some places you treat punctuation as if it's its own word, whether it's a comma or a period, and that kind of is delineating it in here. What's one other thing that may be interesting? Someone who works with language more might know. So there's another option to, I've kept the so-called stop words. Okay, these are very common words that show up in various places, like the. Probably and might be a stop word. Sometimes you would not include a lot of very short common words in here. They occur a lot, and so they really dominate the counts of things, and they're in every possible set you imagine, and they kind of dominate the distance if you're not careful about them. So there's an option to remove all the stop words before you do this, and this is also is sometimes done. I haven't done it here. I think it's become less common to do stuff like this. Okay, but what is really nice about the K2 K-grams is that I'm now the only place that like is showing up, I have it paired with not. So this is a very this document is about not liking something. Okay, so I don't have the word like as the second term without the not in front of it. So I've kind of captured the information that this is a very kind of someone is not liking something. And so that information would not have been captured in the K=1 or in the bag of words. I would not have been able to capture it very well. I'd like to understand, well, what is it that I don't like? I don't like green eggs and ham. This would require a much longer set of K-grams. There are some practices you have K=3 or 4 or 5. If I had 4, I would not like green eggs. Then I would have that whole kind of object in the set. But then it's going to be a lot less likely to have intersections between sets, that I have two things that show up in two documents. That'll be less likely if I make K larger. And so the choice of K is also an important modeling choice here. Let me write this one down. And choice of K. Okay. Yeah.
So basically, kind of what this would figure out is, since there's only one way light comes up and it's not, and then there's also only do not connects to not. So you can kind of get the I do not like by.
That's the idea. You hope that this is your representation of the data. You hope then whatever you're learning on top of it can pick up on the do not and the not like, to imply that there's a lot of not liking going on inside of this document. Okay, this is much less sophisticated than what a kind of a transformer model with activation should be doing, where it has a whole sentence and it's actually kind of it's when you're talking about ham, well, the attention will maybe understand that the not ham is kind of an important thing to kind of encode in the transformer. The attention model is supposedly should pick up these sort of correlations. I'm supposed to piece that together from the string of things, which is a much more kind of not as rich of a representation, but hopefully it's enough to be able to learn something from it. I mean, up until like 5 years ago, so it was kind of one of the best things we had. I mean, there are these these LSTMs, which was kind of a very like a very finicky way to do text understanding and sequential data understanding within natural language processing. But running LSTMs was very hard to scale and to get the parameters right. This was a much blunter thing, but was easier to use ultimately. This ideas existed. People were doing this 20, 30 years ago, and they could get it to work, built entire search engines, entire companies that were really influential based on this idea, and it worked okay. Negation has been hard for a long time. Yeah, but it captured other contexts, like the eggs were green. That seems, if you knew there were green eggs, you probably know who wrote this sentence a little bit. I think Dr. Seuss's estate is pretty litigious, so I did not use this particular example in my book, but I think it's a nice to illustrate it. Okay. Questions? Good. All right, let me see. Yeah, there's also, there was also a time when people would do k-grams with characters instead of words. Why would I want to do it with, and now I've done it with, I've got rid of the capitalization of the words and now the punctuation as well. And now, well, I have all the information in here. I can probably make k equals larger because I only have 26 things in the alphabet after I've removed the punctuation. So I can probably deal with larger kind of charactergrams. This sort of idea actually shows up in use in like genomics. You want to understand consecutive sequences of like the base pairs or proteins and stuff, and things are again stored as sequences. And kind of if you kind of layer these the shingle these k-grams on top of it, you're actually capturing a lot of the information. Those things end up being broken apart and pieced together, and actually finding the consecutive sequences is really powerful. So if you're dealing with genomic data, this sort of idea actually works pretty well. Now people are building transformer models on top of these things instead, which I think probably works better, but I'm not 100% convinced yet. I guess what does AlphaFold do? Right, there's this new, I don't know if AlphaFold does AlphaFold use transformers? Does anyone know? It's this thing that uses sequence of proteins and learns how they should fold in three-dimensional structure. It probably uses transformers, right? Yeah. Okay, so it's probably even somewhat outdated for that, but I think there's still use for it within like genomics. All right, so let's put Jaccard and this k-gram modeling together and see how this works. Okay, so again, let's do k equals 2, and this is the set of pairs of words that show up in these documents. But I want to treat them instead like four different documents. Okay, to give you some examples of using Jaccard similarity here. Okay, so I'm going to have 4 different documents, and these are the resulting shingles or 2 grams for these four documents. They're each represented now as a set, right? As the set of these k-grams, I've converted the data into this representation. And now I can measure the Jaccard similarity between them using, which is defined between sets. Okay, so let's start with Jaccard similarity between the document 1 set representation and the document 2 set representation. Okay, the intersection between them is going to be the I am, which shows up in both. So the intersection, that's D1 intersect D2, the cardinality, that's going to be one item divided by the union between D1 and D2, the size of that, and that's going to be 3 things here. Okay, so the similarity is 1/3. Okay. Yep, that's what I got. Let's do the Jaccard similarity between D1 and let's do D3. Okay. What's the intersection between D1 and D3? Yeah, the intersection between them is 0, so I don't even need to do the denominator. But the size is going to be 1, 2, 3, 4, 5, 6, 7, 9. So 0 divided by 9 is 0. So I says D1 and D2 are not that similar to each other. I am Sam. I do not like green eggs and ham. It rhymes, but otherwise there's not words that are overlapping between them. Right, so I get 0 here. And then, yeah, so let's just, if I do D1 and D4, right, I get 1/8 because I'm going to have an overlap between I am, that's showing up in both of these, right? So that's the 1 here. Okay, and then there are 8 other things. And in general, here's the Jaccard similarity between all of the 4, all the 6 pairs among the 4 sets I have here. Okay, and what it's showing is which are the most similar documents. The most similar ones looks like it's document 1 and 2. They have 1/3 overlap. I am Sam, Sam I am should be pretty similar. And then probably the next most similar are going to be both D3 and D4 is up there. That has, or D2 and D4 is the next most similar, because it's going to have Sam I am in both in this line. So 2 out of 7 things, there's the exact replica of the Sam I am refrain. And then there's the D3 and D4. All right, so this is similar because they have I do not like, right? So there are 3 things which are kind of the same, but it's divided by 11. So it's slightly less similar than D2 and D4. Okay, so this choice of which one is more similar, D2 and D4 or D3 and D4, okay, this is a function of the Jaccard similarity. There are other similarity functions, like the Anberg similarity, the Sorensen-Dice similarity, which I wrote up in the class notes. They might sort these in a different order. They might say D3 and D4 are more similar than D2 and D4. It depends on, it's a slightly different set function, and it may have more stuff in the numerator or denominator. There are other ways you can get it, so it's always between 0 and 1. And so Jaccard similarity is not just like there's L2 distance, which is straight line, and the L1 distance, which is like the Salt Lake City or Manhattan distance. These are different modeling options. They're also modeling options to replace Jaccard similarity. Okay, and that might change the order of these distances. Okay, but hopefully you get a sense that this did a pretty good job of capturing which which of the lines are more similar to each other. And so this was used in, as I said, early search engines. You would feed in whole the text on entire web pages into them. It would build a representation of kind of sets, and it would say which web pages were kind of similar to each other. Or if you have a query, and which will be a string of words, it would say, well, it would treat that as a small set and compare that to web pages that had those words on. How early web pages worked, or early search engines. Yeah. That's how what? Plagiarism detection. Yes, this is how plagiarism detection. There's an option in Canvas I can turn on called, what's it called? Forgetting the name of it, but it can check for plagiarism between assignments. It basically uses this. This is what underlying it, at least the last time I checked. I haven't turned it on in a while. Lots of false negatives for everyone. So some years I had TAs, let's turn this on and see if anyone's cheating. I said, aha, it thinks these things are too similar to each other. I go look at them like these are just people who had similar answers to similar questions. It's not they used the same kind of template or something, and it flagged it. So but this was how plagiarism detection, which is again built into Canvas, worked for 20 years using this notion of similarity between documents for both writing in kind of essays and also for checking in the similar in code. This worked reasonably well for many years. Yeah. Repeated k-grams should not be counted within one document. Okay, so now I wrote them both because I treated these now as separate documents for this example. Within a document, you see it once. In the k-gram model, because we're using Jaccard and because we'll be using minHashing, which I'll describe next, we want to treat them as sets, not as multi-sets. We don't want to do the bag of words sort of count. Okay. Again, there are two reasons for it. One is this minHashing. The other is that with the bag of words model, I needed to predefine this, right? You're all complaining to me, where did I do this? I predefined the set of words, and I picked these 12 words. Why did you include zebra in here, right? I had to pick these set of words ahead of time, okay, to define this vector. I want to be able to compare things. When a vector, if I compare two vectors to each other, I look at particular coordinate and compare it with the other coordinate. The alignment between coordinates, they have a specific meaning, or at least they're directly comparable, is essential for this to work. With sets, this is not the case, okay? And in particular for Jaccard, if we remember the definition of Jaccard here, it's looking at, for every pair I compare, it looks at the size of the intersection over the size of the union. It doesn't care what the universe the sets are taken over from. Maybe it's all 100,000 words I care about, choose 2, okay? That's a huge number of sets. I never need to write that down to compute the distance between them, okay? You can imagine, yeah, okay, so let's, okay, so how would you actually implement Jaccard similarity? How would you, if I gave you two sets D3 and D4, how would I compute the Jaccard similarity between them? Like, how would you think to implement this thought experiment? You would use a set data structure. Yes, okay. All right. What I grew up at a time where I had to implement all my own data structures. So, okay, I was thinking, how would you implement the data structure? Now you would use a set data structure, which would, okay, well, how would you use a set data structure? I would store this in a set data structure and this in a set data structure. abstract it as an array. Okay, good, good. I want to check everything against everything else. Yeah, I want to avoid an n squared algorithm. Okay. So I would probably sort things, right? I would sort everything. I could do it alphabetically by the first term and then by the second term. Okay. What if I sorted things first? Now I have two sorted sets, and I want to check how many total things and how many common things are there. Yeah, well, removing them in a data structure is extra work. I just want to look at them. So I could scan both of them in sorted order, moving the pointer forward if whichever one is smaller, right? And I scan them and I keep track of how many new things I see. And if I see them in both, then I increment the counter for the intersection. If I only see the one, or every time I move one or both forward, I increment the counter for the union, and I scan them. So I have to sort them, but once I sort them, I can do that ahead of time. Then it's linear scanning. Okay. This is not how we're going to advocate to do it, but this is how you could do it, just with Jaccard between two sets. Okay, so I could do it in linear time and the size of the union of the sets. I could, if I pre-computed them in some sorted order. Okay, so it's not too bad, but what I really want to do is I want to say again, I'm running like a search engine. I have one, let's say 1 million, but that's too small. So 1 billion documents. Okay. And I want to do two things. Question one, I want to, on a query, find the most similar documents to the query. Or Q2, I want to do plagiarism checking. So I want to find all close pairs. This is also important for search engines. It used to be you do a search engine and it shows you a bunch of pages that are kind of just, they're the same thing. They are duplicates. They're covering the same information. Where I want each thing on the top 10 page to give me something that's telling me some different information about the search query, because I don't know what I'm looking for, right? So I want to make sure it's diverse. So I want to filter out pairs that are too close, or I want to check for plagiarism because there's two documents that are too similar to each other. Okay. Okay. So I want to be able to do this, but now I've stored all the documents as sets, right? Remember, as kgram sets. Okay, so I want to be able to do this efficiently. So now it's a data structure question again. Promise you it wasn't going to be as much data structure as the last lecture, but kind of we'll talk a little bit about it. Okay, so I'm not going to get into how the data structure works too much today, other than you're using a set recommendation. I'm going to start by telling you about the minHashing, and then we'll figure out how to turn this into a data structure with locality-sensitive hashing kind of in the next lecture. Okay, so minHashing, okay. Okay, so what this is, it's going to choose a hash function from some hash family. Okay, so this is going to be just like we talked about hash functions at the second lecture of the semester, where the hash function, right, is going to go from 2 to the space of all of the kgrams. So it's gonna be all the sets of kgrams, right? So a document is a set of kgrams, and it's going to map it to a real value. Okay, how am I going to do this? And Well, so I'm going to do this in 2 steps. I'm going to create another hash function, h prime, which is from another hash family, h prime, and h prime is going to go from just the set of k-grams. So it's going to take a single k-gram and it's going to go to the real values. Okay, so I'm going to use h prime to define h. So h will be defined, this space here this is the space of documents as k-grams. It's a set of k-grams. That's our representation of the document. But I'm going to start with something that takes a single k-gram and maps to a real value. For this, I can use like SHA-1 or any built-in hash function with a salt, right? And the choice of it is by choosing which salt I put into it. I concatenate with some salt, okay? And so the minHashing will have the property, so it's going to have the very important property that the probability, and this is over the choice of the hash function, that hash function for a document 1 representation is equal to a document 2's representation is going to be exactly equal to the Jaccard similarity between document 1 and document 2. Okay, so I mean the hash function of the property, they're more likely to collide the more similar the documents are under the Jaccard similarity. So if the documents are identical, the Jaccard similarity, at least in the set representation, k-grams, is they're identical, the Jaccard similarity is 1. The intersection will be the same as the union. They will collide with probability 1. If they are disjoint, they have no documents and no k-grams in common, they will intersect with probability 0. If it's like Sam I am and I am Sam, they will intersect, they will hash together with probably 1/3 because the Jaccard similarity was 1/3. Okay. And I did not need, and I will not need to define the union of all the k-grams. I won't need to really define the space. I just need some function that can take a k-gram and map it to a real value, this h prime. Okay, so this is all I will need to do to define this minHashing function. Okay, and hopefully you can get a sense of why this could be useful in finding these things. I kind of do these hashes and the things that intersect are probably similar. Okay, how do I turn that into a day structure is a little trickier, but this is kind of the key trick. I want to create a bunch of these hash functions, and then I'm going to have that use that to find similar things if they hash together a lot. Okay, and we'll cover a little bit of that on Wednesday. How do I put the hash functions together? Okay, so let me describe how the minHash works. Okay, and these are going to think there's going to be a common salt, which is the choice of H, which is what defines H and H prime. Okay, but H will be on the sets of k-grams. H prime will just be from 1 k-gram onto the next. Okay, so how do I define a minHash? Okay. Okay, I'm going to describe this as an algorithm. Oh, it's my son's coming home from school. Okay. Let's see. Okay, so I define a minHash, and I'll call this HJ on S. Call my wife; it'll be fine. On set S. Okay. Okay. So this is well. Let me just not do the J today. We'll Wednesday will create a bunch of these hash functions. Okay, so I'm going to create one of these. And so how do I do this? We're going to have a small algorithm here. So for kind of each element of the set. Okay, so this element could be one of the k grams. Okay. And I'm going to initialize something here. Okay, I'm going to set v equals to infinity. Okay, so now I'm going to say if h prime of x is less than v, then I'm going to say v is going to get this this is h prime of x, right? And so then I'm just going to return v. So this is the algorithm that defines this function h. Okay, so what I'm going to do is I'm going to go through all the elements of my set, all the k grams, hash them into a hash function, my h prime hash function, which is like my SHA-1 or whatever. And it's going to output a value, and I'm going to compare it against some value I'm keeping track of. I set this at infinity, but I'm going to keep track of the minimum value of all the elements I hash to. And this will be my representative. Okay, if I have two sets, I need to use the same h prime hash function. So, and then if I have two sets, document 1 versus document 2, I use the same h hash function. This returns this value v is the output of the h hash function, right? So this means that this v is going to be equal to hash of s. Okay, so this is why it's called minHashing, because I'm hashing a bunch of things. I just take the min object. Okay, so not too hard or complicated to run this. I cycle through everything. I read everything once, pass it to a hash. I just keep track of the minimum value.
So you just save the value.
Yep, just need to store the minimum value.
So will it be just a simple set?
It will only, it doesn't even care which k gram or which element has the minimum hash value. It just needs the value, right? I could keep track of that element, and sometimes you want to do that, but in this case, I'll just need the value. Okay, so what's going to happen is that it's going to choose a value. It's basically choosing a value here at random. Okay, so whichever one happens to be the minimum is a random choice. Okay, and if the two objects, remember so what's the probability so that that two objects are going to have the same minimum value, right? So two sets, what's the probability that two sets will have the same minimum value? Okay, well, what I can consider, so y is the probability that hash of D1 equals to the hash of D2 equals to the Jaccard similarity D1 and D2. Okay, well, so let's consider if I chose what is, let V star equals that the hash of D1 union D2. I took the union of both sets. I looked at V star. Okay, this will always return some value V star. Okay, so how many choices of this V star equals X in D1 union D2. So each with probability 1 over the union of D1 and D2, right? Each element is could be the minimum overall value with one, probably 1 over the size of the union, right? Those are all the options. And so they match if this is the same in both sets. When will it be the same in both sets? When will H of D1 equal H of D2? When they're the same, but in particular in this case, which happens if and only if V star is in D1 and V star is in D2. V star must be in one of D1 or D2, but I need to be in both of them. And when will it be in both of them? This is equivalent to V star being in D1 intersection D2. Right? So they will hash together if V star is in the intersection of V1 and V2. How many options do I get in the intersection? Okay, so that means, which means I have D1 intersection D2 kind of options. Okay, so I have D1 intersection D2 options. Okay, so that means the probability that V star is this is equal to, so that means H1, H of D1 is equal to H of D2. So the probability that this occurs is equal to the D1 intersect D2 divided by D1 union D2. Right? So it happens if I select one of the things in the intersection, the cardinality of the intersection is how many options I have. Each one is chosen with probability 1 over D1 union D2 cardinality. Okay, I add these all up by the law of total probability, and I get this equation, which is exactly the Jaccard similarity between D1 and D2. Okay, so this magical property is why this minHashing gives me exactly the Jaccard similarity. Okay, so I have this clever, fairly simple algorithm that gives me a representation of a set, and I can use it to kind of approximate the Jaccard similarity. I know things collide if they have more Jaccard similarity. And this is kind of the property of minHashing. And then I'm going to run it multiple times with different choices of the H prime hash function, which is used inside of here. All right, and so I can, if I take the average, if I run it multiple times and I count how many times they intersect, that will, in expectation, be the Jaccard similarity as well. If I get enough of them, I get a pretty good approximation. I can use a Chernoff-Hofting bound to kind of tell me how many things I need if I want to do that. Okay. All right, we'll stop here today. In the next lecture, we'll start by talking about locality-sensitive hashing in general, and then how this is an example of a locality-sensitive hash function, which can be used to kind of quickly retrieve either a similar option to a query or to find all the close pairs. We'll see how to combine these together next time, and maybe get into some other sort of similarities and distance functions. Okay, great. We'll stop here. And don't forget to start looking at that first homework question, or the 2A. The 2A. I want to They won't be too hard, but may need a while to get installed. Bye.